Today, let us discuss about the theorems of Pappus guiltiness. So, what is the outcome of the topic? Let us see here. So, the outcome of the topic is to determine the surface area and the solid volumes by theorems of Pappus. And uh, objectives of this topic is we have to derive the theorem of Pappus theorem 1 and to derive the theorem of Pappus 2. And to derive these two theorems, you can find out the surface area and the volumes generated by rotating a curve and plane area. Okay, these are the outcomes and objectives of today's section. And coming to the first theorem, so here the theorems of Pappus guiltiness 1, that is the surface area generated by revolving a plane curve about a non-intersecting axis in the plane of curve is equal to product of length of the generating curve and the distance traveled by the centroid of the curve in the one rotation. Okay, this is the statement of Pappus theorem 1. Okay, now I will explain the statement once again. The surface area generated by rotating or revolving a plane curve. Here, how you get a surface area? If you are taking any curve, if you are rotating curve about non-intersecting axis, then the surface area is generated. Okay, so the surface area generated by revolving a plane curve about a non-intersecting axis in the plane of the curve. So is equal to the product of length of the generating curve and the distance traveled by the centroid of the curve in the one revolution or in the rotation. Okay, so this is a statement. So according to the statement, let us take a plane curve. The plane curve name is a line. Line you consider as a curve. Okay, now according to the statement of theorem 1, here the surface area generated by revolving a plane curve about a non-intersecting axis, right? So let us take a plane of a curve length is L. Now we are revolving this plane curve, okay, about non-intersecting axis is x-axis. So when you revolve this curve about non-intersecting axis, so what is generated here? See here, when you revolve this line, means line is a curve. Now you revolve this line with respect to non-intersecting axis x-axis, then the surface area is generated, which is shown with the blue color, right? This is the surface area which is generated by revolving a line L. Okay, line is a curve. Okay, now according to the statement, now the surface area which is generated, that is area, is the surface area. The surface area which is generated by revolving a plane curve about non-intersecting axis is equal to the product of the length of the curve, generating curve. What is the length of the generating curve? L. Okay, so write down here the product of length of generating curve and the distance traveled by its centroid. See here, this curve has a centroid point. This is the centroid point, right? The curve has the centroid point. Now, the centroid distance from the non-intersecting axis, that is y bar. Y bar is the curve centroid position. Now, the distance traveled by its centroid of the curve in one revolution. See here, the distance traveled by the centroid in one revolution means, so one revolution means 360 degrees. See here, I am taking the 360 degrees. Why? Because if this line or this curve is rotated 360 degrees only, then you will get the complete surface area, right? So that's why here the curve centroid position is y bar and the distance of the centroid traveled in one revolution. So how to get the distance? See here, the angle is 2 the 360 degrees, right? Here the angle is 360 degrees, and the y bar is the distance from the axis to up to the centroid position. Then what is the distance traveled in one revolution? How to find it? This is the perimeter of the curve, right? So that's why how to get that perimeter? That is radius multiply with the angle. The radius is y bar and the angle is 2 pi. So like that, 2 pi into y bar is the distance traveled by its centroid. This is the centroid position. In how many revolution? In one revolution. To get a complete surface area, so we need to multiply with 2 pi. Okay. So like that, you will get the equation according to the statement of the theorem 1 of the Pappus guiltiness. Okay. Now let us move to the theorem 1 of Pappus theorem here. Let us take this is a semicircle semicircular curve, and the semicircular curve you are rotating about the non-intersecting axis AC axis, then the surface area is generated is equal to the product of length of the curve and the distance traveled by its centroid in one revolution. Okay, that is the statement. Similarly, here you are taking the inclined line as a curve, and if you are revolving around about a non-intersecting axis, then the surface area is the cone surface area you will get. Okay, cone. Okay, this is the cone surface area, and here the surface area is generated is sphere. Why? Because if you take a semicircle curve rotated around a non-intersecting axis 360 degrees means complete rotation, then the shape will be the sphere. Okay, in that case the shape is a cone. And the third case, if you take a curve, circular curve, and you are revolving it about non-intersecting axis, then the surface area generated is a torus surface area will be generated. Okay, these are the surface areas generated by revolving the plane curves, okay, in the same plane. Okay, so that is about the theorem of Pappus Berlinus 1. Okay, so according to the theorem of Pappus theorem 1, you can calculate the surface area. You remember that here when you are revolving the plane curve, you did not get any volume, any solid part. Why? Because only curve part only you are rotating about non-intersecting axis. So you can calculate the first theorem to find out the surface areas, not volumes. Okay, so you remember that. Okay, now coming to the proof of the first theorem, let us take the one curve here. The curve name is ABC. So I am taking the name of the curve. See, this is the name of the curve, ABC. ABC is the name of the curve. Now we are rotating that curve about non-intersecting axis, that is x-axis. It is rotated about x-axis by an angle theta. So how much angle we have to rotate this one? So we are rotating this one with an angle by an angle theta. Rotate this one by an angle theta angle. When you rotate this one, the surface area is generated. See, this is the surface area generated. This is the surface area is generated when this curve is ABC curve is revolve about an axis, an x-axis, about x-axis by an angle theta, then the surface area is generated. Okay, now you need to find out the surface area generated by revolving the curve ABC. Okay, now how can you find the surface area generated by revolving a curve ABC by using the theorem of 1. So that's why here first to find out this one, first you take a small element length. See here, I am taking the small element length. So take in that surface area, you consider one small element. This is a small element, right? The length of the element is dl. Dl is the length of the element. Why we took the dl differentiation term? Why? Because the length of the element is too small. So consider it as a differentiation term dl. And what about the width of the element? See this distance. Okay. What about the width of the element? The width of the element you can find out how because here the y may represent the centroid distance from the x-axis. Okay, from the x-axis to up to the element y. Y means the centroid distance of the small element curve. Okay, y means what? It is the centroid distance of the small element curve from x-axis. So now this centroid distance is traveled up to theta angle only. See here how much angle we rotated here. The centroid of the element. This is y the centroid position of the element. So that is rotated how much distance? The centroid of this element is rotated only theta distance. See here, it is rotated only theta angle. So then what is the length of this? What is the width of this element now? This is the centroid distance. The centroid distance, how much it is moved? It is moved only theta angle. So that's why the width of the element, you will get the y into theta. Okay. I think you understand how you will get the width of the element. Anyway, length we assumed as a dl. Why? Because it is a shortest distance. sorry, the two small distance we represented with the differentiation term, and the width of the element we consider we are considering by taking the centroid distance moved through an angle theta. Okay, the centroid of the element curve is y, and y bar is the entire curve centroid position. Okay, you remember that y and y bar. Y means centroid distance of the curve, means centroid position of the small element from the x-axis. Okay, y bar means centroid position of the entire curve, not for a small element curve. Okay, that is the difference. Now coming to this one, first you find the dA. DA means you know that is the element area. How to get the element area? Element shape is the rectangular shape. Length into width we know as a element area. The length of the element is dl, and the width of the element is y theta. So L into B will give the element area. Okay, length of the element is dl, and y into theta is the width of the element. If you find the element area, then if you do the integration for the element, suppose I want to find out the total area. How to get the total area? If you know the element area, if you integrate that element area, then you will get the total area. Why? Because the total area, if you want to find out, this area is made up of infinite number of element areas. So that's why to cover the total surface area, we are doing the integration for one element. Okay, by applying the integration. Okay, now the element area will get by applying the equation, that is integration into dA. Anyway, dA you know that is dl into y into theta. So in the place of the dA, substitute the value dl into y theta. Okay, this is the integration dA value. Out of this value, theta is a constant value, move out of the function now. So write down here the theta out of the function, and the integration y into dl. Okay, this is the integration y into dl. Now in that equation, now theta into, so integration y into dl. Now you multiply with the l. See here, you multiply with the l and divide with the l, capital L. Okay, multiply with the capital L and divide with the capital L. So there is no change in the function value. Why we are doing? Why we are multiplying with the same value? Why? Because here in the L place, if you are multiplying with L and dividing with L here, the function will be integration y into dl. This is the first movement of area of the, means first movement of length divided by total length. It will give the centroid position of entire curve. Okay, integration y into dl into capital L means distance. You are multiplying the small element with distance. So that is the first movement of length. First movement of length divided by total length will give the centroid position of the entire curve. So the centroid position of the entire curve is represented with the y bar. Okay. Now in the second step here, you write here, move the theta outside, and L, anyway here L is there, you keep it outside, and in the place of the function you write down the yc. Otherwise you can also write the y bar. Okay, so like that. So here the finally you will get the 2 pi. Theta means here this is theta only if the area is rotated only theta angle. But to cover the complete rotation means what is the total angle? 360 degrees. So we should write down in the place of the theta is the 2 pi, and the remaining terms, the y bar is the centroid position of entire curve, and L is the length of the curve. So hence the theorem has proved here, according to the theorem 1, that is the total surface area generated by revolving a plane curve is equal to product of length of the curve and the distance traveled by its centroid in one revolution. Okay? So that is the statement of the theorem of Pappus-Guldinus. Okay, and it is very very important. And I'll move to the next theorem, that is the theorem of Pappus-Guldinus 2. Okay, now the theorem of the Pappus-Guldinus 2 that you can use to find out the volumes of the solids, right? How the volumes of solids are generated. Okay, let us see the statement of the theorem 2. Okay, the volume of the solid generated by revolving a plane area about a non-intersecting axis in the plane is equal to product of the area of the generating plane curve and the distance traveled by its centroid of the plane area during the rotation. So this is the statement of Pappus theorem Guldinus 2. Okay, now once I will explain the statement. Here the volume of the solid generated by revolving a plane area. So here we have to take a plane area, and the plane area is revolving about a non-intersecting axis. Then the volume of solid is generated. Okay, so that is the meaning of the statement. The volume of the solid generated by revolving a plane area about a non-intersecting axis. See, let us take a plane area. Here the plane area is capital A. Okay, now this area is revolving about a non-intersecting axis, x-axis. X-axis a non-intersecting axis now, and it is revolving about a non-intersecting axis. Then the volume will be formed. See here, when the area is revolving about non-intersecting axis, then what is the shape you will get? The shape will be the volume. Okay, suppose if you revolve a curve, the surface area is generated. If you revolve the area, the volume will be generated. Okay, that is only the difference. Okay, now the volume of the solid generated by revolving a plane area about non-intersecting axis in the plane. The plane means you should take the plane in the this area in the same plane, means xy plane. Okay, is equal to product of area of the generating curve. So what is the area of the generating curve? Capital A. See here, the volume generated by revolving a plane area about a non-intersecting axis is equal to the product of area, means it is multiplied with A, and the distance traveled by its centroid. See, what is the centroid position of this area? The centroid position is represented this with respect to x-axis. The centroid position always represented with the y bar. Okay, now what is the distance traveled by the this area? Means the distance traveled by its centroid in one revolution. See here, the centroid position of this area is y bar. Now the y bar, it moves 360 degrees, means one revolution, one complete revolution. If it moves one complete revolution, the total angle is 2 phi. Okay, complete revolution angle is 2 pi, and the radius is represented with the y bar from the axis to up to the centroid position y bar. Then what is the distance here? How to find the distance? Y bar into 2 pi will give the distance traveled by its centroid in one revolution. So that's why here the y bar into 2 pi is represent the distance traveled by its centroid. And which centroid? Plane area. Distance traveled by its centroid of plane area. Otherwise, the distance traveled by the centroid of the plane area during the rotation. During the rotation means one rotation you have to take. That one rotation it will give the angle 2 phi. Okay, this is about the theorem of Pappus Guldinus 2. And now let us see some example. Here the sphere area is rotated. Means here the semicircle area is rotated. The solid will be generated is sphere. And here the triangle area is rotated with respect to non-intersecting axis. The cone solid will be generated, and the torus area, this is the area. So torus means here the circle area is rotated with respect to some distance from the non-intersecting axis. The torus solid will be generated. Okay, so this is about the theorem 2 explanation. And according to the theorem 2, the body of revolution is divided, means generated by rotating a plane area about a fixed axis. So that is 2 pi into y bar into A. That is the volume. Now let's move to how to prove the second theorem. And coming to the proof of the second theorem, here let us consider the AB is a plane area, ABC is a plane area. See, let us take the ABC is a plane area. This is A, B, C. This is a plane area. Now this plane area is rotated through an angle theta. See, this plane area is rotated through an angle theta. So how much angle it is rotated? Theta angle is rotated. So when it is rotated theta angle, what is the shape you will get here? Here the solid shape you will get. Why? Because you are rotating the area. So that's why the entire shape will be the solid. Okay, now how can you find the solid volume? By rotating the plane area by applying the theorem 2. So now according to the theorem 2, to prove this one, first you should take one element first. So I am taking one element. See, I am taking one element. This is the element. and this is the front face of element. So the front face of element I represented with the element area is the front face I am represented with the element area dA. This is the element area is dA, this element area. This is the front face, okay? But what about this is the three-dimensional plate. Three-dimensional plate means it has a thickness. See, this is the thickness. It has thickness, okay? And how to get this thickness of this element plate? Okay, this thickness you will get here. Starting here, how much angle it is rotated? Let us take similarly y is the centroid of the element plate, not for entire area, for only element uh, area centroid. Element area centroid position is y bar. And how much distance it is rotated here? The starting it is rotated theta angle. So then what is the thickness of this element plate now? The thickness of the element plate is y theta. Okay, if you take a element like that, the element. Now anyway, the front face area is represented with the dA, and only the, if you are seeing, this is the thickness, three dimensional. So how you get the thickness here? The centroid position of this element plate is y from the x-axis, and how much it is rotated? Theta. So what is the distance traveled by the centroid of the element area? That element area centroid is traveled at a distance of y theta. Okay, y theta will be the thickness of the element plate. Now, what is the, we should find out the volume. So element volume. So how to get the element volume? Element volume is equal to element area into thickness of the element. Okay. Anyway, element area is represented with dA, and thickness is represented with the y theta. Okay. So write down the y theta is the thickness of the element. Okay. Now, if you want to find the total volume, that is V is equal to integration dV, means integration element volume. You are doing the integration for the element volume, then you will get the total volume. Okay. Now here in that theta is the constant value, so move the theta is outside. And the remaining terms are y into dA. Okay. Now in that term here, if you are dividing this function with a and multiplying with the function with a, then there is no change in the total function. See here, your numerator is a and denominator is a, so then there is no change in the function. When you're writing this equation here, if you observe that integration y into dA by a, what do you mean integration? Y into dA by a. Okay, y into dA represent the first movement of area. Okay, the first movement of area with respect to which axis? Here y used, so that's why with respect to x-axis. So y into dA is the first movement of area divided by total area. So the first movement of area divided by total area means centroid position, right? This is the formula of the centroid position from which axis? From x-axis. So that's why from the x-axis, centroid position is represented with yc, otherwise y bar. Okay. Now, in the place of the yc or the y bar. So write down the, in the place of the yc, y bar, and the theta is the 2 phi. Why? Because if it is rotated, the complete rotation 360 degrees. So in the place of the theta, you can substitute the 2 phi angle, that is the 360 degrees angle, and yc we have written as a y bar, and a is there. So like that, according to the theorem of Pappus volume generated by revolving a plane area about a non-intersecting axis is equal to product of area and the distance traveled by its centroid is the product of area and the distance traveled by its centroid in one revolution, that is 2 phi. Okay, this is the proof of the Pappus theorem 2. Okay, and let us see some examples for the theorem 1 and the theorem 2. Now let us find the surface area of the sphere. So how to find the surface area of the sphere? First, how to get the sphere area? By revolving a semicircle curve. Okay, so first, if you want to get the surface area of the sphere, so how you get the surface area of the sphere? According to, if you are revolving a semicircle curve about a non-intersecting axis, okay, then you will get the surface area of the sphere. Okay, now the surface area of the sphere, that is capital A, is equal to the surface area of the sphere, capital A, is equal to, according to the theorem 1, surface area generated by revolving a plane curve about a non-intersecting axis is equal to the product of length of the curve equal to the product of A is equal to the product of length of the curve. Sorry. The product of length of the curve and the distance traveled by its centroid. Y bar is the centroid distance of the curve. In one revolution means 2 pi. Okay. This is the formula of the theorem 1, right? According to the theorem 1, the surface area capital A is equal to L into Y bar into 2 pi. Then here, what is L? Length of the curve. So can you find what is the length of the semicircle curve? What is the length of the semicircle curve? So the semicircle is making an angle, phi angle, 180 degrees, and the radius of the semicircle we have taken as a capital R. Then what is the length of the curve? So radius into angle, that is R into angle is phi, 180 degrees. So this is the length of the curve. Okay, take the length of the curve is R into phi. The place of the length of the curve R into phi. And what is the Y bar? Y bar means I told you centroid position of the entire curve. The curve name is semicircle curve. What is the curve centroid position means? What is the Y bar centroid position? 2R by 5. 2R by 5 is the curve centroid position. So write down here 2R by 5. This is the curve centroid position, semicircle curve centroid position. Here the curves also having the centroid positions, but the curve syllabus we don't have in our syllabus, so we didn't discuss in our class. Only the area centroids only we find in the last classes. Okay, the formula of the semicircle curve centroid position is 2R by 5, and here anyway 2 phi is the complete rotation angle 2 phi. In that phi cancelled, and what is the remaining thing? 2 into 2 4. 2 into 2 4 is there, here pi is there, and R square is there. So 4 pi R square. See, this is the surface area generated by revolving a semicircular curve about non-intersecting axis. That surface area shape is the sphere shape. Okay. And coming to the second theorem, I will give one more example. So to get the volume of the sphere, how to do? Means you can find the volume of the sphere by revolving the semicircle area. So take a semicircle area here. The semicircular area, it is showing the capital A is the semicircle area. This is the semicircle area. Now this semicircle area is revolving about non-intersecting axis x axis. Now the volume generated by revolving a semicircle area is equal to, according to the theorem 2, that is the product of area of the semicircle and the distance traveled by its centroid in one revolution. The centroid is represented with y bar, y because this is x-axis. Suppose we are considering the y-axis, then the centroid position according to this one, you should take x bar. Remember that here the non-intersecting axis is x-axis, so the centroid distance is in terms of y bar. Okay, and y bar into the centroid distance traveled by its centroid in one revolution. One revolution means 2 pi. Okay, this is the formula of the volume generated by revolving a semicircle area. Okay, now what is A? A means area of the semicircle. What is the formula of area of the semicircle? Pi r square by 2. This is the formula of the semicircle. And what is y bar? Y bar means the semicircle area centroid position. What is the centroid position of the semicircle area? Okay, that is 4r by 3 5. But the semicircle curve centroid position is 2r by 5. But in the case of the area, the semicircle area centroid position, that is y bar equal to 4r by 3 5. And here 2 5 is there. And 5 cancelled, and 2 cancelled. The remaining will be 4 by 3 pi r cube. So 4 by 3 pi r cube is the volume of the sphere. Okay, so like that you can calculate the volume of the sphere by revolving the plane areas by using the theorem of Pappus Goldinus. Okay. These are the derivations of the theorem 1 and the theorem 2 of the Pappus theorem Goldinus. These are used to find out the surface areas and the volumes by revolving a plane curve and the plane areas. Okay. So this is about the